What's going on inside your phone or your computer? I mean, it can feel like pure magic, right? But it all boils down to just a few basic building blocks and some rules that are, honestly, surprisingly simple. So today, we're going to pull back that curtain and demystify the world of electronics.
Here's our game plan. First, we'll figure out what electronics even means. Then, we're going to meet the humble resistor. It's the real workhorse of control. After that, we'll look at the two basic ways to build a circuit, introduce the resistor's cousin, the capacitor, which stores energy, and then, finally, we'll see how all these simple pieces come together to create the incredible complexity we see all around us. So, let's jump in.
All right, first up, what are we actually talking about when we say electronics? Well, the whole idea really comes down to one single powerful concept: control.
I mean, think about it for a second. A toaster and a tablet both run on electricity, right? But a toaster just takes that raw power and makes things hot. That's its whole job. A tablet, though, a tablet thinks. It processes information, it connects to the internet. The real difference isn't the electricity, it's the absolutely insane level of control we have over it.
And that's the key distinction right there. Electrical tech is all about generating and moving raw energy, like the power lines coming into your house. But electronic technology, that's about the precise control of that energy. It's about manipulating the flow of tiny little electrons to process information. That control is the secret ingredient that makes everything from your laptop to a satellite work.
So, how do we get that control? Well, we start with the most basic, most common component in the entire electronics toolkit: the resistor.
This little guy might not look like much, but I guarantee you'll find thousands, maybe even millions of them inside the devices you use every single day. It is the absolute fundamental workhorse of electronics.
So what does it actually do? Well, a resistor, just like its name suggests, resists the flow of electricity. A great way to think about it is like putting a valve on a water pipe or pinching a garden hose. You're not stopping the flow completely, but you are limiting how much can get through. And that simple act gives engineers incredibly precise control over the current anywhere in a circuit.
And what's inside is surprisingly simple. A common one is just a mix of carbon dust and a ceramic binder. The more carbon you have, the easier it is for electricity to flow, which means less resistance. Some of the more advanced ones use a super thin metallic film, and a laser actually cuts a little spiral groove in it to fine-tune the resistance to an exact value. Pretty cool.
Okay, so how do you know what a resistor's value is? Well, you've got to read its secret code. These little colored bands aren't just for decoration. They're like a secret language that tells an engineer everything they need to know. The resistance value, the multiplier, even its tolerance, which is how accurate it is. It's a simple, universal system for controlling the flow of electricity.
So we have our first component. Awesome. But how do we actually connect it with other things? It turns out there are two fundamental ways to build a circuit, the rules of the road, if you will, and it's super important to understand them because they behave in completely different ways. First up, we have the series circuit. This is where you connect components end to end, kind of like a daisy chain. The most important thing to get here is that this creates only one single path for the electricity to flow. There are no detours, no side streets, and that has some very specific results.
Because there's only one path, the consequences are pretty straightforward. The current flowing through every single component is identical. Calculating the total resistance is easy. You just add them all up. And the voltage from your power source, it gets split up and divided among all the components in the chain.
The second way to do it is a parallel circuit, and this is a totally different beast. Instead of one single path, a parallel circuit gives the current multiple branches to choose from. Think of it like a river splitting into several smaller streams. The current flows to a junction and then divides itself up, with some of it going down each available path.
So the rules here are pretty much the opposite of a series circuit. First, the voltage across every single branch is identical. The total current flowing is just all the branch currents added together. And here's the kind of weird, counterintuitive part. Adding more resistors in parallel actually lowers the total resistance. It's like opening more checkout lanes at a store. More paths means less overall opposition to the flow.
Okay, so we've got resistors to control the flow, but the electronics toolkit has a lot more to offer. Let's meet another key player, the capacitor.
So if a resistor acts kind of like friction, turning electrical energy into heat, a capacitor is more like a tiny rechargeable battery. It doesn't really resist the current, it stores it up. It holds onto electrical energy and then releases it exactly when the circuit needs it.
At its heart, a capacitor is incredibly simple. It's just two conductive plates separated by an insulator. That's it.
When you apply a voltage, positive charge builds up on one plate and negative charge builds up on the other. This separation creates an electric field between the plates, and that field is how the capacitor actually stores energy.
And why is this so useful? Well, capacitors are everywhere. They're used to keep the memory in a device alive for those few seconds while you're swapping out a battery. They smooth out dirty or noisy power to make it clean and stable for sensitive components. And they're absolutely essential for things like tuning circuits, like when you're dialing in your favorite radio station.
All right, so we've got components that resist and components that store, and we've got two basic ways to connect them. Now, let's put it all together and see the big picture.
And this right here is probably the most important takeaway of all. There is no magic. Every single incredibly complex electronic device, from your smartphone to a space satellite, is built from a handful of simple components just like these, all connected together according to the basic rules of series and parallel circuits.
This is the power of scale. A few resistors and capacitors can make you a simple little radio tuner, but when you combine millions or now even billions of them on a single microchip, you get a device capable of unbelievable computation. The real genius isn't in the individual parts themselves, but in the staggering number and the clever arrangement of all those simple, fundamental pieces. And this kind of leaves us with a fascinating thought, doesn't it? Our entire digital world is built on a foundation of just a few simple components, like resistors and capacitors. If these basic building blocks have managed to take us this far, just try to imagine what's going to become possible when we discover the next one.